It is estimated that 8 million metric tons of plastic enters our oceans each year. 20% of these plastics come from offshore platforms and boats. The rest is blown into the sea from inland. In some very polluted areas of the ocean, the mass of plastic exceeds the mass of plankton by 6 times. This is because many plastics don't biodegrade and will collect together due to the currents in the sea. An example of this is the Great Pacific Trash Patch, which is around the size of 3 UKs. Plastic in the ocean is problematic for birds. When some plastics are left in the sea, they start to release a chemical called dimethyl sulfide, or DMS for short. This chemical is also released when zooplankton, a shrimp-like organism, eats phytoplankton, like green algae. Some seabirds use the smell of the DMS to locate the zooplankton, because where there are zooplankton, there will also be fish. The DMS produced by the plastic will falsely alert the birds to a food source. So consequently, seabirds eating plastic is very common and can be fatal. In a 2019 study, it was found that 13% of the birds tested had ingested plastic. But ingestion isn't the only threat that plastic causes to birds and other wildlife. Entanglement in plastic can cause injuries, suffocation, and can reduce the capability of animals catching prey, which could lead to starvation. To truly understand the problems caused by plastics, we must understand more about them first. So what are plastics? Plastics are polymers, which means many parts. These parts are called monomers, as represented here by the orange circles. There are two main classes of polymer: natural, like DNA and cellulose, and synthetic, like the polycarbonates that some plastic bottles are made from. But how do polymers form? There are two mechanisms: chain growth and step growth. Chain growth is a mechanism that adds monomers one by one from a starting point. In this demonstration, the blue circle represents an initiator molecule that starts the polymerization process. From this starting point, monomers are added one at a time to the chain. This stage is called propagation. The reaction can be ended through a termination step, or when all the monomers are used up. In this case, the end of the chain will still be active, so could still react with another monomer of complementary reactivity. The step growth mechanism is a bit different to the chain growth mechanism because it doesn't require an initiator. Each monomer can react with another monomer to form a link, providing they both have functional groups that react together. Here you can see that dimers have been formed from groups of two monomers. This can happen randomly within the system as monomers get close enough together to react. Eventually, longer chains are formed, like this trimer. In some cases, if monomers are multifunctional, branches can be formed within the chains. This can drastically change the properties of the polymer. The mechanism ends when there is no longer anything else to react. So we now know how polymers are formed, but do they break down back into monomer units? Well, some do over time, under certain conditions. There are 4 mechanisms for this. Firstly, through contact with a chemical oxidant. This can result in bonds breaking in what is known as the polymer backbone, when oxygen is introduced. This causes the polymer to split into chunks and will disrupt any intermolecular interactions occurring between the polymer chain. Secondly, photooxidation. This is a reaction of the polymer with air, particularly oxygen, under the exposure to visible and UV light. The light increases the rate of production of radical species, which speeds up the initiation to the degradation process. This mechanism is limited to the surface layer, but as the surface layer breaks off or cracks develop, the lower layers can be oxidized too. Thirdly, a process called chain scission. This occurs without the need of a chemical oxidizing agent. The molecular structure of the polymer is changed when under stress or raised temperature. Due to this, covalent bonds in the polymer backbone will break randomly, so the molecular weight of this polymer rapidly decreases. Finally, hydrolysis. This process is the breaking down of a polymer by the contact with water, which is constantly the case in the sea. This is due to the presence of the component ions H+ and OH-, which act as acids and bases. Step growth polymers are particularly at risk of this mechanism because the way the monomers join in polymerization is through condensation reactions. This means the bond is formed between the monomer and the chain by the removal of, typically, water. Therefore, the reverse of this reaction is to add water back, which will break the covalent bond in the polymer backbone, thus breaking down the polymer as a whole. When these plastics break down, they will leach the subunits into the water, which are potentially toxic. A case study for this is polybisphenol A, a polycarbonate that is used in many everyday products such as food containers, CDs, bicycle helmets and protective eyewear. The monomer, bisphenol A, or BPA for short, has been found to interfere with the reproductive systems of animals. In a 2014 study, BPA was found to reduce the levels of testosterone in the blood of rats treated with the monomer. BPA may also have a detrimental effect on the female reproductive system. The structure of BPA is often said to be similar to the hormone estrogen, so therefore BPA may inhibit the processes that estrogen controls. A 2003 study investigated the factors that increase the rate of degradation of poly-BPA. It was found that the rate increased when temperature increased and when the environment was at pH 8. When I was at the beach, I decided to test what the pH of the sea was. I found that the pH was around about 8. Therefore, the poly-BPA will break down faster when in the sea, opposed to if it were inland and out of water. In summary, plastics are a negative addition to our oceans, and so we should do as much as we can to avoid them getting there.